Get your merch.
No.
Everything under control?
Yep.
You still chat for people on YouTube asking questions?
Yeah. This is good. Yeah. Type 5 or type 6.
Thank you so much.
There you go. Not too far to go. Yes. Every once in a while, we take it on. Okay. And it's
Or 86, 87, 88, 89, 90.
Down a lot.
So we're on YouTube or screen sharing. Thingy is here.
Okay, if we can, everybody can find a seat. Is this thing on? Pardon me, Jeremy. Okay, we're going to get rolling now. There you go. Thank you.
Oh, that's not fun. Yeah, I was saving the seat for.
Welcome, everyone, to the May meeting of the Delaware Valley Amateur Astronomers. My name is Tom Delasco. I'm the president. And I'm glad you can make it out tonight. We have a good lineup happening, so let's just get started. I usually choose one or two pictures each month that are kind of an interesting shot. And these couple shots, there's actually three shots, there's one following this, but they're really cool shots. The one on the left is by Bill McGeaney. He took it at Raystone Lake, is that how you say it, Bill?
Oh, Raystone.
Raystone Lake. Never been there, in central PA. And it kind of reminded me of the shot Bill took last year in the winter over a frozen lake with the snow coming in. But it's a really nice kind of skyscape image there. He was testing some equipment out. And then Alan Purdy, we mentioned last month about the moon and Venus being close together, and Alan out there and could catch it, I assume from his backyard. And got a nice shot down there with the moon and the crescent moon and Venus. Where's the right there? Oh, okay. Okay, and then this is I think, I don't know if Sandy said this or somebody said this on the IO groups, Dan's deep field. And that really looked, and I thought the exact same thing. Dan Stern took this is 28 and a half hours of data through a 17-inch telescope with a very large sensor down in Chile. And it was a remote image. And it reminded me, as soon as I saw it, reminded me of the Hubble deep field image. And if you were to actually blow this up, especially the original, there's just galaxies everywhere. And Dan said more than 1,000 faint galaxies are visible across this field. So it's very, very, very reminiscent of the Hubble deep field. That's just a beautiful shot. It's Able 1736. Some of those galaxies, really faint ones, are not part of the Able group. They're background galaxies, but he's going very deep here. Okay. Every month I talk about Jupiter and Venus and Mercury and the moon, it seems like. And we have a close encounter here on the 9th. Venus and Jupiter are 1.5 degrees apart, which is going to look pretty neat in the sky because they're the third and fourth brightest things in the sky. And also, that same night, down below here, it's kind of in the trees here, is Mercury. So if you have a clear horizon, you can get all three of these really easy. A pair of binoculars will help for Mercury, pull it out. And once you spot it, you'll be able to put the binoculars down and take a look at it. But back in April of 22, I happened to be out at Cherry Springs. And the Venus and Jupiter at that time were a little under a degree apart. And I went over to the field across from Cherry Springs, actual observant field, because it had much better horizon. And what I had mistakenly done is I forgot first off that we were so far west, more further west, so it got brighter half hour later. So I got out there nice and early and just waited around. But one of the things that was really neat about that, I'm walking across this field. This is like a Friday morning, so it's like overnight Thursday. And I cross this field, it's like 5 o'clock in the morning. And I can hear people who are just campers out there, just out on blankets looking at the sky and saying, oh, there's this constellation, there's that. Oh, did you see that meteor? It was just a neat thing to have all these people up just in the blackness. You couldn't see anybody, but you could hear voices, you know? And it was really a neat little thing. It was like a little community there. It was a lot of fun. Anyway, this will be an interesting thing. So the 9th, if it's clear, you check this out. We kind of watch the progression here as this goes on. Like on the 8th, 9th, and 10th, Jupiter's going to be dropping and Venus is going to be going up, so they'll pass each other. Venus will be below Jupiter when the 8th, and it gets closest point, and then it'll be much further up the next night. Okay, this is the star of June, the occultation of Venus, daytime occultation, and look where this thing is. That is due south. At this appearance, and it is almost at the highest point in the sky. It's over 60 degrees up. It's really ideal. And now the moon's thin. It's 2 days old, and that's a good thing and a bad thing. It's a good thing because it's kind of neat because you can still be the dark side of the moon, the unlit side, will be occulting Venus, and so you can look. We'll just see this. You'll be able to pick up in a telescope. You may not even be able to see this in a telescope in the daytime because it's not that far from the sun, about 38 degrees from the sun, and but this should be a really cool event. It starts at about 3:50 is the disappearance. A little after 5 o'clock is the reappearance. And but Venus is not that big, 14.6 arc seconds at the time, and about 74% illuminated. But one word of caution here, I think it's a good idea to use a telescope, but if you got a pair of binoculars just to kind of find it in the sky, because it's a thin moon, pretty close to the sun like that, it's going to be a little tough to see. But be real careful if you're using binoculars and like scanning for it, because you don't want to accidentally, cross it in front of the sun, because you'll be very sorry if you do. But anyway, this is the premier event. But there's more. That night, the thin moon, which had really nice Earthshine at that time, is going to pass through the Beehive cluster. Now, it's not going to be that high in the sky. You can see it here. This is, it's just, you're in very deep twilight type of situation. But you should be able to see the Earthshine should be really prominent. When the moon is this narrow, the Earthshine is beautiful. And with a pair of binoculars or a telescope, you should be able to see the stars, some of the Beehive cluster as it passes through it. So that'll be kind of a neat thing to see. Okay, this is your challenge object. This is really probably more of an astrophotographer's thing, especially like a smart telescope, see stars, or the dwarf. What you have is comet 10P Temple, periodic comet, is going to pass within about a degree of the Saturn Nebula, and it'll be about the same brightness. They're both about magnitude 8. That'll look pretty cool. And for the larger field of view, if you have a little larger, like the S30 Pro or a Dwarf Mini, might be large enough where you also can pull in the globular cluster 72 and the open cluster 73, M73. But this could be, it's close from about the 28th to the 1st, right in here. But that could be cool. It's gonna be tough. Now here's the gotcha. It's an almost full moon. so that's kind of this is where the challenge part comes in. But if you wait till close to dawn, the moon will be low in the southwest, quite low. And this will be up highest, pretty high in the sky, a little bit east of the meridian. So I think that's the time you want to try to snag it if you're going to do that. But, okay, waning galaxy season. This is June 1st. You can see southwest now is no longer in the southeast or the south. The whole galaxy area here is starting to, 10 o'clock at night, it's nice and dark then, but it's starting to go down. June is still a good month. Look at the galaxies. July gets trickier. Every day that goes by gets trickier and trickier because they're lower in the sky, and you're looking through more atmosphere, and it just gets harder to see. And the odds are your light pollution is gonna be much worse there, even if you're at a semi-dark site. So this is the month. This is your last hurrah to get a good glimpse of some of these galaxies. But the good news is we got a lot of really bright spring clouds. There's tons of spring clouds, but this whole group here is up June 1st. You can get all these guys. Pretty much as soon as it gets dark. And they are as they are across 3, 5, 10, 12, and 13 to Hercules, 14 and 92. So that's kind of a fun thing to go hunting down. Now we have some observing news from Jan Rush.
You will have to do, yeah, the size of it.
Yeah, okay. You want to take a hand sign or this?
I guess. Okay,
You want your slides?
I do. No, not yet. Okay, so we have some good stuff coming up this month. I'm Jan Rush, by the way, I'm observing chairperson. So we're going to have a dark sky telescope clinic for beginning and intermediate observers at Green Lane Park. It's June 5th. We'll start at 8:15, and we have 2 backup dates. So hopefully we can get it really right this time. The backup dates are June 6th and 7th. And you need to register for this because the way these clinics work is that we ask you exactly what telescope you want to get help with, and make sure that there's a person there who knows that telescope and can help you out with the questions that you've got. So we'll make you work a little bit to answer the questions before you register for the clinic, but you'll be glad you did. There's still time to register. And also we have a camping event to announce. We'll be camping as a group at Cherry Springs Park on the astronomy field. So this is not the Big Dipper Lodge. This is back actually on the astronomy field at Cherry Springs. We have an event window of July 11th through the 16th. And basically we're going to look at the weather and then, check with each other and decide when the best days will be to actually go. I don't think we'll actually be there that long. Cherry Spring never has that many good days in a row, but that's the window. So you could put the window on your calendar and keep in touch to find out what the actual dates are. So for any of you who don't know what it's like to camp on the astronomy field at Cherry Springs, there are tents available. I mean, you bring your tent, there's tent camping available or RVs. And on the Cherry Springs website, there's all the information you'll need about what the field is like. And you can also talk to basically any member that's been around a while, has been there multiple times. We do want you to register because then we'll know kind of how many campsites we need to reserve not reserve. You can't reserve them ahead of time, but the first person that gets there will kind of try to block out some adjacent sites. So take a look and consider coming. And when you register, you don't need to know for sure that you're coming because you're not paying any money. It's just letting us know that you're interested. Okay, I now have one of the great jobs of being observing chair, and that's to present an observing certificate. So Al, would you like to come up, please? So everybody here, I'm sure, knows about the Messier list, and that's the list of 110 objects that Charles Messier was able to see with a 4-inch telescope in the late 1700s. And what? what the Astronomy League has done is they've established a different list. Well, they didn't establish the list, but Lewis Smith, who was an astronomer in the late 1800s, he worked on a list of objects that hadn't been found yet, as far as he knew. A lot of deep sky stuff. And many of those objects eventually made it into the new general catalog, the NGC or the IC. But when he discovered them, he thought he was the first to have found them. So he found over 1,000 things that he thought were new, that had not been discovered before. And what later astronomers did, they found some duplications, they found some stuff that wasn't really new. So now there are 798 objects in the SWIFT catalog. So the Astronomy League, along with Al, decided to develop an observing program to find those 798 objects. And Al is patient zero. No, he's observer zero, the first one to earn the certificate, which is for 100 of the objects. And then you're going to work on the other 698, right? And these objects, so I forgot to mention, were with a 16-inch telescope in the late 1800s. So Al, here's his certificate. The Swift Observing Program. Oh, yeah.
One more.
Does the number say 0 or 1?
Says 0.
0.
Oh.
Actually, there's 3 of us had 0, because
Oh,
we helped with the development. And a lot of it was I've seen before, so I had to go through my database and extract all this stuff. And he wanted to know, was it easy, moderately hard, or very hard, and what telescope, et cetera, et cetera. So
Is that easy by your standards or normal standards?
they're subjective.
Yeah.
They're tough. They're from Green Lane is tough. Yeah, they're small and the 12th magnitude, but they're small. That makes it a little tougher.
And it comes with a nice pin.
Yeah.
All right.
Oh, yeah. Thank you. All right. Next.
Okay.
yeah, what's the list called?
Swift list.
Okay. Brian, you're up. Oh, yeah.
My name is Brian Lee. I'm the welcoming chair for the DVAA. We have 9 new members this month. Chris Worthington, Brian Whittington, Elliot Borgman, Shirley Lambert, James Locke, Benjamin Arsati, Logan Landau, Enid Chavez Thies, and Henry Sendeka. And those last 4 are part of the Youth Awards group of this year. There was one more, but she hasn't contacted me yet, so hopefully next month. Make them welcome.
Okay. Thanks, Brian. So, if you haven't seen it, we have some 50th anniversary merch. DVAA was started in 1976. We have some stickers, magnets, refrigerator type magnets. They're like 2 by 3 inches each. The stickers are good to hand out to people to if you go to a store party, and if you want to if there's some couple kids there, you want to just give them a sticker, they'll be glad to get it. And there's embroidered patches, badges rather, kind of thing, and they're in the back, and with Brett and Jen. And so look at them and pick something up. And there's been we're in discussions of trying to have some kind of luncheon. But it's still kind of cooking there on the back burner. We're trying to work some of the details out. But of the people here, how many people would be interested in attending a luncheon on a Saturday? Okay. Very good, thanks. So,
Tom, is there an exact date or an approximate date?
well, we're trying to come up with that.
I meant
Depends
for
on,
the club,
for
for the club's formation.
I went back. The club was originally the AGCO, Association of General Celestial Observers, and in '76, I have a hard copy, green and white computer paper printout, was what they used to send out. It was just in snail mail, and it had a copy of the Constitution and a vote thing on there back in '76, and that was in January, I think that was sent out. But it seemed like they were still referring to the AGCO up until about July. It seemed like, so by August, it was definitely there. And July might have been the first month where everything was totally changed over. But it was in the transition period from the beginning of '76 to at least that time frame.
You should get Ken Burns on the case.
Yeah, really. There are a few documents, actually, I think up on the website, under historical documents, like the original Constitution, maybe some of the letters, and
Who was our first president
Bill Schuman formed the club.
and the club?
He was AGCO, but he broke off. There was some,
But when it came to DVAA. who was the first
that was
president?
Bill Schuman. So, yeah. So, upcoming events, a couple of these we talked about, but we'll go over them again. Tomorrow night, Radnor's Great American Cookout at the Willows. If you want to come out and help Barry and Jan and a couple others, come out, just even if you're just coming out just to support them, not bringing any equipment, but
And I've offered to bring the club solar telescope out from 4 to 6 tomorrow.
very good. That's great. So it's good to support this because they're the ones who have this hall for free, which is a pretty remarkable place to meet. So anyway, but if you're free tomorrow night, just come out and pair of binoculars, come out and join the crew. Okay, Jan mentioned the observing clinic on the 5th, primary date, rain dates. That's a Friday night, Saturday and Sunday are the rain dates. It's a great place if you're new to astronomy, you have trouble with your telescope, you're trying to figure things out. You had a scope in your closet for years and not sure what to do with it. Bring it out and people can help you get yourself rolling. The Cherry Springs Star Party, that is actually closed I think it's all filled up, long since filled up in hours. But for anybody who's going, it's still on the 14th. Public Star Watch, June 20th. We have our 4th one. We got rain down in May. But so hopefully this will be a better time. School will be out. It should be a good crowd. It's a great June, July, and August are really good times for the Star Watches. Then we have the astrophotography workshop. It's a Zoom meeting. It's the Wednesday before the main meeting. These are really interesting. I'll talk about this with another, I got a slide coming up, but we just mentioned that there is if you're interested in astrophotography or thinking about it, please join into the Zoom. Our monthly meeting's the 26th at the end of June. And then July, you have what Jan was talking about, the DVAA at Cherry Springs State Park, and you have Green Bank Star Quest. They're not quite overlapping there completely. So you could go to Cherry Springs for a couple of nights and then shoot down the Green Bank is about 6 hours roughly from here. And I checked before the meeting how far it was from Cherry Springs. It's about 6 hours, about the same thing. So it's a pretty good haul, but you could do both. At least get down there. I heard Green Bank is a great star party. Everybody's been there has raved about it. And our public star watch in July 18th. Loaner equipment. We got a new piece of loaner equipment. there was some requests made to Joe Lamb about binoculars, and we didn't have a pair of binoculars to lend to people. So we purchased a set. So we have a 7x50 Skymaster, Celestron Skymasters, and they're coming in Monday, I think Joe said.
So,
In Arizona. Joe, you want to stand up and we can look at you and know who to contact? That's Joe Lamb.
Cowboy hat. And
Yeah.
work the truck. There's some city slickers back, so, coming in Monday to Tuesday.
Yeah, so if you're interested,
So,
that joins our complement, and we have 4 smart scopes and a 5th semi-smart scope. This one here uses your cell phone, and you kind of have to point it. It's not real smart, but it kind of zoops up your cell phone. And now we got the binoculars. We have several visual scopes, these 3 here. And we have the solar scope, which if you haven't used the solar scope, they can be a lot of fun. You can see the chromosphere of the sun versus the photosphere, and things happen quick. They happen in minutes versus days. Okay, now the AP workshop. Okay, so it's a little bit different each month. It usually starts out, we have a first half hour, 7 to 7:30. We have a beginner. So anybody who's new, they can come in there, ask questions, just even the most basic question. If you even are thinking about astrophotography, even in the future, come on and join us. There's a lot of people in this club have a lot of different talents in astrophotography. We're really well stocked in this club with astrophotographers. And we all lived through the beginning from not knowing anything to progressing onward. And so feel free to come out and join us. It's not intimidating. We don't laugh or snicker at you or anything like that. And there's this coming in June, there's going to be a short present after the initial beginners Q&A. Gary Trapezzano is going to give a short presentation on his acquiring and processing a shot of the Great Hercules cluster M13. He had a nice shot that he did some comparisons of different, shooting things in his backyard versus shooting things at Hickory Run State Park, for example. And then we always have a show and tell in the end where you can show pictures, new equipment you got, and just do projects you hope to work on. We've had people make, the own tracking mounts or spectroheliographs and all kinds of things. But it's an interesting period to share and see other people's equipment and their images. And this is where you can find, you guys go to the website and go to June, you pick up the 24th there, I believe it is. Yep. And you hit that and you'll get this, and just click on that link and you're good to go. I'll take you right to it. Okay, now we have a reserve report. The lights are out. Once again, Jan Rush.
Right, me again. So, in March, I made a trip to the Canadian tundra to see the Northern Lights. And I sent some pictures into the groups.io, and people said, hey, we'd really like to hear a little more about that trip. So I put this talk together because it was kind of interesting, a little bit different than the usual observing trip. So we went to Churchill in Canada, which is up here on Hudson Bay. And it's pretty cold there. It's billed as the most accessible place in the world to view the Northern Lights. I don't know if that's true or not, but that's the advertising. So the gateway city is Winnipeg, which is the capital of the province, the Canadian province of Manitoba. And from Philadelphia, you get there through Toronto or Ottawa or Montreal, basically. So we flew into Winnipeg, and then there's a a flight to Churchill, which is about an hour and a half. Churchill was actually founded in 1717, and it was the home base of the Hudson Bay Trading Company. So all the animals that lived up there got these nice thick furs, and they did a lot of trading there, and that's how the town was formed. Some of you may remember it because it was also pretty famous in 1769 during the Transit of Venus. It was one of the three main locations where they tried to determine the Earth-Sun distance based on parallax from those three areas. And it was two British astronomers who went there. It took them more than a year to get there with all their equipment. But that's another thing that why Churchill is famous. Also, it was really first famous not for Northern Lights, but for the polar bears. Something about the way the Hudson Bay is geographically, or is the topography of the bay, that area freezes first of the whole bay. And so then when it freezes, the polar bears can get out on the ice and find seals after having nothing to eat for most of the summer. So they come through Churchill, these I don't know if they're hordes, but there's a lot of polar bears that come right through Churchill, waiting for the ice to form so they can go out and find their seals. So that's how it is most famous, actually, is for polar bears. So here's the 2-engine prop plane we used to get there. Here's downtown Churchill, 600 people live there. Here's a little blizzard they cooked up just for us. It was pretty brief. And this is the view from the place where we stayed. It was a lodge, very, very desolate, because they want you in a place that'll be dark, because you don't want the lights of the bright city of Churchill to ruin your aurora viewing. And this is the sign announcing the lodge. It's called the White Whale Lodge. And out here is Hudson Bay. So very desolate area. So here we are. We were at 58 degrees north. This is my husband Skip and I. And somebody took the screenshot of the temperature. So around midnight, when we were seeing a good aurora, it was -23. And the wind chill, which is very relevant because it's really windy, was -45. Yeah. And the town of Churchill has a good sense of humor here. Here's what they call their weather station. It's a rock suspended from a cord. And it says, if the rock is wet, it's raining. If the rock is blue, it's cold. If the rock is gone, it's a tornado. So here we are. These are this is the getup that they give you. Insulated boots and snow pants and a big parka and lots of stuff that goes underneath. So they take good care of you.
So this was a group you were with?
It was Natural Habitat sponsored the trip. You can do it on your own, but it would be hard, actually. Yeah, there are 3 restaurants in town. So you have to figure out a way to eat. So why Churchill? Well, as I said, it had the tourist infrastructure. There was a military presence in the US base at a Canadian base, mostly active during the Cold War and after World War II. It's not active now, but it means they have a nice airstrip. And it's actually a pretty decent airstrip. Polar bear tourism got the excitement going, and then they said, well, maybe we can make a tourist, maybe we can use the tourists maybe we can use the aurora to attract tourists during a different season of the year. So they say they have auroral activity 300 days a year, but of course, if it's not real dark, it's not really very impressive. So you have to go when it's dark. which they say the best aurora viewing is January, February, and March, because the skies are dark, the bay is frozen, and so it increases the chances that you'll have clear skies. And the polar bears are way out in the frozen bay searching for seals, so they're not going to bother you. And this is not a small thing. When the polar bears are in town, the locals have to leave their cars unlocked so that if you happen to see a bear going by, you have a car to duck into. Nobody goes jogging or walking during that part of time. And this was outside our lodging to remind us to check our surroundings. But at least when they're in January, February, and March, they're all out on the ice, and they're really not there to bother you. But we did have a guy with a rifle who was with us when we were observing.
How many bears did you see?
None, of course. They're gone. They're out on the ice. They did have some stuff for us to do during the day. We did dog sled riding and snowshoeing. That's me and my warm stuff. And they had us do an art lesson with pastels. We drew the aurora. Okay, now let's get into the good stuff. So I think everybody here knows that the solar wind is mostly the result, or is the result of energized particles that leave the surface of the sun when there are flares, when there are coronal mass ejections, when there are coronal holes. And most of them are deflected by the magnetic shield. So they'll just go that way. But there's a weakness in the shield that kind of directs them toward both of the poles of the planet. So we have the aurora borealis and the aurora australis. It's interesting that the auroral oval surrounds the magnetic pole, not the geographic pole. Here's the geographic pole. And this photo from NOAA is a kind of composite that's showing the energy levels of the auroral oval. And you see there is a kind of especially bright area, and here's the Hudson Bay here. So I believe it when they say that the lights are quite bright there, maybe compared to other places you can see them, Alaska, which is here, Iceland, which is here. So I like this photo. It's a little bit old, solar cycle 32, but you can see this. These are photographs from NASA, and you can see how the 11-year solar activity cycle plays a role very much in what you can see in the way of aurora. So this is the solar maximum in solar cycle 32. It was 2001. Pretty good activity on either side well, for 1 year, maybe 2 years, but this period here is of very low solar activity. Is going to have a lot less in the way of beautiful aurora. And here we are this year. Our solar cycle peaked in October of 2024. And here we are in 2026. We're still reasonably high in the number of sunspots, but we're on the downslope. Okay, these pictures are from one of our members, Prasad. I asked him, what did the sun look like when I was in the tundra? And this is what it looked like. So that's super, super exciting. NOAA calls this magnetically low complexity in the sunspots. So if I had known this, I couldn't have changed the dates anyway. But the day after we left, a corona hole. Oh, well. All right, I'm going to show you a couple of things we saw. So this is a photo I took the first night, and you can see how very subtle, really, the lights can be sometimes. It was pretty, but it wasn't like super, super exciting. And if I can get this video to run, while we were looking at these not so very exciting lights, somebody was showing us this, which happened a few days before.
What is that? What are we doing?
Yeah, that TP is what they put up to basically to give you some something to photograph while you were in the area of where those lights were. Yeah, so we like that. Replay it? Oh my goodness, I'll just send it to you. Now, day number 2, we had some pretty bright stuff. And that's the title I used here, "The Lights Are Out," doesn't mean people have turned out the lights. It's what the locals say when the lights are out. It means go out and look at the aurora. It's out there. It doesn't look super bright green like the photos look. I mean, just like here, we know that the sensors on our cameras pick up way more color than you're able to see with your eyes. But it was very impressive because of its movement and its breadth all over the sky.
Cell phone?
Pardon?
Cell phone photo? Cell phone?
Yeah, cell phone, any kind of photo, any kind of camera actually picks it up. So, I mean, here's an example of it. It was just all over the sky, moving in curtains. And then this little place here is a nice little warm place they give you to go in and warm up and give you some hot drinks.
How long is the exposure?
Oh, it's you can vary it obviously, but once you get beyond about 10 seconds, then you start to see dragging of the stars. So we weren't going really long, but. So see if I can get this to run. Yeah, this was our lodge. And so you could just go outside and this is what you'd see. This is a time lapse though. This is speeded up.
How fast?
I don't know how fast the time lapse is. And this shows you, this is the horizon, obviously, where the trees are, and it shows you how broadly the aurora extends across the sky. Get this one to. Again, this is time lapse. They gave us all tripods, so it's a big forest of tripods. Everybody was a photographer. Now here's one that is not time lapse. This is maybe I could get that down here. No. There we go. This should show you what you could see real time. And you do see movement. And we could see the color of this on that night. That's me saying, I see some.
Now, was it like all over the sky or just one?
Every permutation. Sometimes it was just several waves. Sometimes it was all over the sky. It was different every night. We observed for 4 nights. And then when we weren't looking at the aurora, I gave an impromptu astronomy lesson there with my laser at their request. So this is one of my favorite pictures. It was taken by one of our guides. And I was thinking when I put this up for my astronomy club to see, somebody's going to ask me what those constellations are. It's probably going to be Mitch Berger. Or maybe Dave Mitski. And I couldn't figure it out. So I brought some other people in on the problem. And Al couldn't really quite see anything that jumped out at him either. So we thought, let's ask AI. And so here's what AI had to say. Who can tell me what's wrong with this picture? Oh,
Everything.
Yeah, just a quickie, here the pointer stars of the Dipper are not pointing at Polaris, it's way down there. At 58 degrees, Polaris should not be this low, it should be way up there. Draco isn't contiguous with Perseus, Cassiopeia doesn't have the right relationship to Andromeda, Cepheus is upside down, everything is wrong. So we thought that was really fun, and we actually tried, this was ChatGPT, we tried a bunch of AIs, and they never got it. So we brought Gary Trapezzano onto the case. And Gary loves a challenge, right? So he took the picture, the original photo. He used the metadata from the iPhone. This was taken with an iPhone, by the way. Metadata from the iPhone, Wikipedia, Stellarium, and then plate solving with PixInsight. And an hour of work, right, Gary?
Yeah.
This is what it came up with. Yeah, so this is what we got. And I think it's the combination of the aurora in the background is just changing the brightness of everything. It just doesn't look the way it usually looks. But here's Andromeda, and actually, right, kind of where the D is. If you blow up the photo, you can see kind of an oval, blurry thing that's the Andromeda galaxy. Yeah, see it.
Yeah.
Yeah, and we have some Messier objects in there too. So this is from the last night we had quite a lot of red naked eye aurora. It was only there about 15 minutes. So you do 4 days and 4 nights of observing, and you see one night when you see a lot of red and green naked eye, but it was still fun.
And Jen, remind us what the green is, excited eye.
Yeah, the green is oxygen, green and white is oxygen.
And red.
And the red is nitrogen. And sometimes nitrogen is blue. I meant to tell you that. Good. Thank you for that. So I don't know if anyone wants to go. Sky and Telescope says they still have 2 trips that are open to Iceland or Finland and Finland. I think it's going to be, I have to get in this solar cycle soon because we're going to be low activity in a while. Oh, we did ask our guides, when was the best stuff you've seen here? And when on that day in October when we had just amazing auroras here, that was also a fantastic night for them.
2024.
Yeah. That was one of their best nights ever.
Hey, Jen,
Mhm.
how did you guys do shooting it when it's what, -20?
Yeah, it was hard.
So how long were the cameras out? How long?
Yeah, they kept going bad. When they had a place to warm up, you could plug in, and we just had to keep plugging in. Yeah. Well, and we switched out batteries, and we went from the iPhone to another camera, and it was like shove like juggling.
You bring in a lot of batteries. So.
Oh yeah. Yeah. Okay, that's all I got. Yes.
In these photos, what was the cloud? Were these crystal clear nights, no cloud cover?
Yes, they were crystal clear nights. Yeah.
Jen, did you use a smart telescope like an S12 Pro for this?
I think it's too narrow.
It has a wide lens.
Well,
Too cold.
too cold, yeah, a combination, I guess. But yeah, you have to have a really wide lens, so I don't know what the capabilities are of all the cameras out there.
I'm gonna need power. Do you mind? Yeah.
Switching computers over.
Yeah. Fine. One camera there. Is right? I know. If you want, you can turn the air conditioning. Pretend.
Does that work?
Yeah. Okay, so camera on the north. Yeah. That's great. It's all skies.
So we get set up. I'm Jeremy Carlo, the programs chair. So a little bit about upcoming programs. Next month, we're going to have our very own Ken Koplinger is going to be presenting on 250 years of astronomy in the US, both stars and stripes. So just in time for July 4th. In July, we'll have another of our returning champions, Bart Freed, coming back for a presentation. And in August, yet another returning champion, we'll have Steve Connard, who's given some presentations on New Horizons and Pluto, and more recently on light pollution. This time, I think he'll be talking about occultation timing. So you have a couple of good presentations coming up. Tonight, we have Dr. Matthias Fabry from Villanova University. So Matthias comes to us from Belgium. He completed his undergraduate and graduate degrees at KU Leuven. Did I say that right?
You did, yeah.
All right, close enough. And since then, he's been a postdoctoral researcher at Villanova. So his interests are in binary stars, particularly contact binaries, where the two stars are very close together, and massive stars, which have interesting late-stage evolution. So please join me in welcoming Matthias Fabry.
You have the other. Oh.
You
Do I
that
have
one.
to use that one?
Oh, yeah, that's probably easier.
All right. Let's see. There we go. There we go. Yeah, I think that works. Great, thank you, Jeremy, for introduction, and thank you for having me. It's a great pleasure to be standing here in front of you. I think I moved to Villanova about 2 years ago. And I must say that even within the state of Pennsylvania, the amount of things that you can see is so much larger than what you can do in Belgium. Not only because of the size, but also because of the light pollution you can get in the more central, closer, higher central parts of the state. So yeah, as my presentation is titled, main interest is in contact binaries, but before we do, before we get there, and now I have to probably click here, yeah. Let's start by talking about stars, and actually the introductory meeting you already had is a great segue into my presentation, because you know better than me probably when and where you best see a lot of stars. So this is the sky you would see tonight. Obviously, it's a full moon, so you all know better than most to actually go next week when the moon is not that prominent. And there you can see the galaxy, and we know now that galaxies are collections of stars, typically in the order of 200 billion to more 400 billion stars in our Milky Way, and almost essentially every single point you see in this image is a star. There are, of course, deep sky objects like clusters and can I move this OK bar thingy?
You'll be able to click on the OK.
Let's just go here. And then play again. Sorry about that. Essentially, all of these are stars, and as being stars, they dictate essentially the evolution of galaxies and indeed our universe. The best known star, again, as we know, is our sun. And we know its properties very well. It's the best studied star by far, weighs about 2 × 10⁻30 kilograms. And we patched this symbol 1 solar mass next to it. I'll use that throughout the talk. It's a very commonly used unit. We know its size pretty well. It's about 700,000 kilometers to the photosphere. Of course, that's around 300,000 miles. And if you put Earth next to it, it's obviously barely visible. It's all the way down there. It's about 1,000 times or 100 times smaller in radius. 1,000 times, sorry. And we know now, since 1925, what the sun is made of. It's mostly hydrogen and helium with only trace element of what we call metals or heavier elements. Everything that is not helium or hydrogen is called a metal, which I'm sure must confuse chemists quite a lot. But that's what we do because there's orders of magnitude less metals than hydrogen and helium in the sun. And this is opposed to what people thought of the sun having a composition much more like the Earth, which has much more iron and silicate oxides and so on. But thanks to Cecilia Payne, we now know that is not the case. And by extension, essentially all stars are made up of hydrogen and helium. So rather than looking at pictures of the sun, which is nice, let's actually make a star. And I got this recipe, which I got from my mom. She's a good cook. And she tells me to, okay, let's take a large pot, and for every 3 parts of hydrogen, I have to add 1 part of helium. Okay, so I take my pot, put it on the stove, take 3 units of hydrogen, 1 unit of helium. Let's put that in. Next part is add a sprinkle of metals. That's what Cecilia said. Okay, we only need very few of these heavier elements. So let's take our salt and pepper shaker, put in some carbon, nitrogen, iron, titanium, lithium, all that stuff. And then the next part is arguably the most important one, is that we have to stir using a gravitational spoon. This is quite a special spoon that my mom has. Because when we stir up this material, all of that mass that we added, and it's a lot of mass, obviously, will start gravitationally attracting each other and condensing into what is a hot ball, because the recipe even warns us that it will boil spontaneously and give off a lot of heat because of gravitational energy being turned into thermal energy. So we don't even need our cooker. And in fact, the recipe is so easy, we don't even need an oven, because this will self-regulate. Nuclear burning in the sun turns hydrogen into helium, and that essentially makes the sun live for very long periods of time, more than it takes to just collapse all of that material. So that's it. We made a star. It's essentially a ball of gas that wants to collapse, but in doing so, has an extreme temperature and pressure in the core, and we can calculate how much that is. It's about 10 billion degrees, excuse me, at the core of the sun. And that is hot enough to allow for fusion of elements from hydrogen to helium in the first stage, and then to further elements in later stages. And that very process stabilizes the collapse of this huge hunk of gas and creates something that we call hydrostatic equilibrium, where the sun is actually, or the star in general, is not contracting or expanding at a fast or appreciable rate. Now, of course, in real life, we use magical spoons and pots to make up stars. In real life, in nature, it happens in these molecular clouds. These are huge light years across clouds of dust and gas that start collapsing and form new generations of stars. And in fact, in this is a James Webb Space Telescope image, one of the first ones, released in 2022, I believe. There's already a set of stars to the north of this picture that are massive enough to actually start blowing away the gas southward. You even see these little streaks here of dust essentially that's being pushed down by by all of this intense radiation coming from the massive stars in the north. So let's move to stellar evolution. Now that we've made stars, we can understand how they evolve. And as I mentioned, it's a continuous fight between gravity and the production of energy. And on the main sequence, this is done by fusing hydrogen into helium. And that takes 90% of the lifetime of the star. And in that sense, or in that phase, most of the stars line up in what we call the main sequence. This has been observed by the Harvard observers back in the beginning of the 20th century, I believe. The sun is here in the middle for reference. It's about 6,000 Kelvin or 5,700 degrees. 5,700 degrees Kelvin at obviously 1 solar luminosity. But this series is essentially a mass sequence. Less massive stars are dimmer and are cooler. Higher mass stars are more luminous and hotter on the main sequence. Now, when all of the hydrogen has been burned, most stars move on to the post-main sequence, which takes the remaining 10% of the life. And then the stars start lining up on the giant branch where stars are getting really, really big, but relatively cool compared to normal stars. Obviously, there are still low mass stars in the main sequence that are also cool, but they're definitely not as luminous. Betelgeuse, for example, is one of the most well-known supergiants. So it would appear on the top right corner here on this diagram. The main takeaway from the evolution in this diagram is that because the structure of the star needs to adapt to its new properties, for example, when hydrogen turns into helium, the pressure of this gas and the properties of this gas change, and the star has no choice but to become bigger in order to maintain this balance, this hydrostatic balance. And the sun is no different. And in fact, the sun has already become about 10% bigger than it was born with and 20% more luminous than it was born with. And that's interesting to note that, life evolved during the time in which the sun was much weaker. And I guess biologists and as geneticists as well have to take that into account when tracing the evolution of life, for example, on our planet. Now I'd like to point you to several differences in evolution of low mass stars and massive stars. So whenever you have a stellar object that is more massive than around 10 times the mass of the sun, we call it a massive star. On the main sequence, it's very similar. They both burn hydrogen and they both slowly get bigger over time. But what is different is how long they can do this. You could say that, oh, well, if this star is 10 times more massive than our sun, wouldn't it live 10 times longer? Well, no, because gravity, in fact, is so strong in the star that it has to burn its fuel at a much, much quicker rate in order to maintain its hydrostatic balance. And that's why it only lives for about 30 million years compared to the sun's 10 billion years. So it's a steep function in lifetime as you go up on the mass scale. And that's very general. So the more massive the star is, the faster it will start evolving. That'll become important when we talk about binary evolution. On the post-main sequence, that's where most of the differences between low and high mass evolution occurs. Both stars will turn into some sort of giant. This we call a red giant. Sun will become a red giant. And the massive star, again, like Betelgeuse, will become a supergiant, as we say. And the differences lie in what kind of nuclear burning they can do. Low mass stars will stop at carbon and oxygen in the core, whereas massive stars go all the way to neon, silicon, and eventually iron. When the sun is done burning, it will go into a planetary nebula such as M57. I'm pretty sure you all know where this is located on the sky. And this is essentially the outer layers of the star being slowly ejected into space, and whatever remains in the middle is a white dwarf. You can't see that, at least not in optical wavelengths. On the other hand, because iron is the most stable element, and no fusion can occur beyond that, the fight between gravity and internal pressure is essentially over, and gravity wins, collapsing the whole star into a neutron star, which is like a very hard pit, if you will, where all of the other gas essentially bounces off of that, and together with a neutrino burst creates what we call a supernova, core collapse supernova. And sorry about that. Damn it. And that created the Crab Nebula in, what was it, 1054, our guest star, I think it was called by Chinese astronomers. And now we have the beautiful Crab Nebula. And if you look at this in radio or in X-ray, you can actually see the neutron star somewhere here in the middle, which is active in these high energy wavelengths. So massive stars in particular are very important to look at because they violently eject lots of new metals, materials that have been built inside the star into their environments. And that is how, and this is what in part contributes to galactic evolution. And this is sort of the summary plot that Jennifer Johnson from Ohio State compiled in tracing back where all of the elements come from in our solar system. So for example, I like to look at oxygen. Oxygen corresponds to green. So these are all coming from massive star supernovae. So you can think about how every oxygen molecule that you and I breathe, or every water molecule which contains an oxygen that we drink, is eventually traceable to the explosions of previous generations of massive stars. And that's quite spiritual in some sense, right? The same goes with sodium, for example. Every grain of salt that you put on your food has come from massive stars. Carbon, on the other hand, which is the main ingredient of life, is in part coming from these slow ejections of low mass stars, but also a good chunk of exploding massive stars. So our quest as astrophysicists is really to understand how stars evolve, how they live their life, and then how they die, contributing to how elements get made and build up over the course of the life of the universe. Now let's move to binary stars. And when I make this talk, I usually think about what would be the most well-known binary star to you people. And I think Sirius is probably one of them. I think with a fairly modest telescope, you should be able to see Sirius B, as long as the seeing is good enough, obviously, because it's reasonably close to the main star and the contrast is not too big. But Sirius is a main sequence star, but it has a white dwarf companion, which is much weaker or dimmer next to it. There's Alcor and Mizar in the Big Dipper, of course. You should be able to distinguish them with the naked eye. In fact, I think it was used as a diagnostic test for one's eyesight at one point, if you could resolve Alcor and Mizar. But I think the most well-known binary star is actually this one. This is Tatu A and Tatu B, pretty well-known binary star. And I usually think, often I think about how life would have evolved if instead our planet would be hosted by two stars rather than one. And actually, if it were like this, it wouldn't be much different, I'd say, because this star is much weaker than that star. And the amount of energy that this planet would get from the sun is pretty similar, actually. So this would be perfectly stable over millions and even billions. All right, so the next thing we need to wonder, though, is when we see a binary star in the sky, are these actually related or not? Because it could be, and in this case, it is most likely the case that Alcor and Mizar are actually totally unrelated. They're pretty far apart. They will never sort of interact with each other. But it could also be, in other cases then, for example, like in Sirius, that the stars are really close by. And this is what Herschel, back in 1802, distinguished between, this is where Herschel distinguished between what we now call optical doubles and actual binary systems. So this is a little passage from his paper where the most important text is here, mutual gravitation toward each other, right? So we call binary stars only real systems or real binary stars when they are gravitationally bound. rather than just appearing next to each other on the sky. Okay, before going into actually studying binary stars, we need to know whether they're actually common or not. And this is where we point our telescopes to a whole bunch of stars across the sky and actually just start counting. There's different techniques in how to determine whether a star is actually a binary. I won't go into those here. But after doing all that data analysis, and this is decades of work, this picture has sort of arisen out of that effort, where it shows that for stars roughly the mass of our sun, it appears that about half of them have a binary companion next to them. So like Tatooine, for example. When you go to lower mass stars, so this is almost the brown dwarf limit, only about 20% have a binary companion. But massive stars really win out, because when you go to the massive regime on the right-hand side of the diagram, essentially all of them, like 95 to 100% of massive stars, have a close companion to them. And that really changed the way we think about how massive star evolution works, because in the way I explained to it in the beginning, that was how we think a single massive star would evolve, rather than how a binary massive star will evolve. So a lot of research in the last 10 years or so has been devoted to understanding how binary interaction works. And I want to introduce this topic by considering the following. Say you have two masses orbiting around each other. And then you ask yourself the question, where would the combined gravity of these two objects pull other objects? Say you have another small parcel, maybe like a planet or something, and you place it somewhere here, where would it fall to? And that's where the Roche potential comes in. This is discovered or described first by Edouard Roche, French mathematician, and he constructed what is now called these Roche potential or Roche equipotentials that essentially tell you that, okay, if I'm inside of or very close to this first mass, I will obviously fall towards M1, the first mass here. On the other hand, if I'm close to M2, I will fall toward the secondary mass. And if I'm somewhere in between, then I guess I can float around maybe. And importantly, if I'm beyond the points of L2 and L3, I will actually drift away, because this whole system is spinning, obviously. And there is some kind of centrifugal force acting. Also, there's Lagrangian points where these are balanced points where you can, in principle, sit indefinitely, although L1, L2, and L3 are unstable. So you need some station keeping to keep you near that. For example, in the Earth, moons, is it the Sun-Earth system? James Webb, for example, is located at L2 of the Sun-Earth system, where it actually needs very limited station keeping to stay inside of the shadow that the Earth casts. So that's for thermal reasons. Finally, one extra term I need to introduce is the Roche lope. If we consider or restrict ourselves to just this figure 8 here, the zone that M1 dominates, let's say, is called the Roche lope of that star. And then obviously M2 also has a Roche lope. And that, again, will become important later. So let's now combine what we know about stellar evolution and binarity, and let star 1 evolve. This one is more massive. It starts out larger, and so it'll evolve faster than the right-hand star, and this should play, yes. So as it becomes bigger, it essentially fills up its whole Roche lope, and then in principle, it will continue doing that, because the Roche lope is not a physical wall or something. It will continue to expand, and then there will be this mass particle here on this little hill, which is unstable. Again, L1 is unstable. So of course, it will start falling over this ledge into the well of star 2, and we get what we call a mass transfer event from a donor star to an accretor star. And note that this will change the properties of both stars dramatically compared to what single star theory, evolution theory would predict. in some popular articles, this gets compared to like stellar vampirism. I personally don't like this this wording, because this sort of wants to this tells that the accretor star has a lot of power here, but it doesn't, because it's the donor that decides to give mass to the accretor. So I like to reverse the order here and call it maybe blood donation or something to stay in theme, and get like a patient or whatever. So a little less fantasy oriented. Okay, now binarity in massive stars is extra important. Like I mentioned, on the right-hand side of that diagram, 100% of, roughly 100% of stars are in binaries. And from carefully studying the periods, so how far the stars are actually orbiting around each other, we now know that 30% of those are so far apart that they can effectively live their lives as if they were single. So they can expand and grow without doing this mass transfer kind of situation. But that does mean that the other 70% do. They do get born close enough together to interact. And then, for example, with this large envelope stripping part of the pie here, that's where this donor that becomes stripped when it donates material to the accretor. Accretion and spin up is the other side of the coin. This is the stars that get material from a companion. And then in a quarter of stars, interaction is so extreme that they'll actually merge. So mass transfer doesn't have to be stable all the time. When it does get unstable, you go into a merger situation where previously you had one star, but now you have one because one of them gets torn up by tidal forces, essentially. And it turns out, by doing careful calculations from my countryman, Jan Henneko, that 40% of those, so most all of these, and then I guess a part of a combination of these, go through a contact phase, and that's what you continue to see in the background, where you have essentially two stars overflowing their Roche-slope. This looks pretty much like this. I can, I guess, pass this around. This is a little model I made from W. Yuma. This is the potential associated to it. You can also pass this around. And on that little mock-up, this 3D print, you can see two parameters: the mass ratio of the system, and the filling factor is essentially telling you how far this contact binary is overflowing its Roche-slope. So there's a lot of them out there, but models of those, so again, to understand how massive stars live and how they seed the galaxy, for example, we need to really take under consideration all of the potential physics occurring in such stars. And yes, colloquially, we do call them peanut stars because that's exactly how they look. So sometimes we laugh about them. Now let's go through the scenario of actually making one of these binaries that is currently being passed around. And what you do is you start with two massive stars in a 1.4 day orbit. So on the left-hand side, we have 25 solar masses, the right-hand side, 17.5. And the period, so the orbital period of these is 1.4 days. So please do, please try to imagine what an orbital period of 1.4 day is. I mean, the Earth goes around the sun in 365 days. Mercury does so in 88 or something. The moon goes around us in 28 days. But no, in this case, you have two absolutely gigantic stars, way more massive than the sun, orbiting each other in 1.4 days. And that needs velocities of something like 400 kilometers per second.
How far apart are they?
Several solar radii. At most like 5 solar radii or something. Extremely close. I also note here on the top the mass ratio. So this is just M2 divided by M1. This is indeed to scale, as I just explained. Now let's start. Oops. Let's go back. Now let's have stellar evolution again do its thing. The more massive star will evolve first, or the fastest, and it will grow first to fill its Rochlot. Obviously, it doesn't stop there, so it initiates mass transfer with its companion. A whole bunch of mass is now being transported from A to B. The mass ratio has flipped, so now we have a mass ratio here greater than 1. And you might have noticed that there was already a very brief contact phase here where 2 stars were touching, but that phase is not really observable because it goes over so fast. You don't expect to actually see stars in that phase. Next, we have what's called a slow mass transfer phase, because the left-hand star is still the most dominant star in the system. It still wants to expand. But in the meantime, because this star has now become more massive, it also needs to evolve more quickly and starts growing. And when both stars reach the Rochlot, you get into what's called a long-lived contact phase, where indeed we expect stars, where we indeed expect to observe stars in this way. So we have again 2 stars. The period will have probably shrunk to around 1.2 days or maybe 1 day. And this can live for millions of years, so essentially the lifetime of a massive star. Now, because the right-hand star has become more dominant, eventually the masses will become equal, roughly equal. And after that, the system will probably merge. They will merge into one star. And this is one of artist impression of one of the most famous, at least in our community, contact binaries in the Large Magellanic Cloud. This is VFTS 352. They have roughly equal masses. Both stars are about 30 solar masses big. It's very blue, obviously. And this one orbits, I think, in around, I think it was 1.4 days or something. So this is a very well-studied system. And we know its size and its mass very, very, very accurately. So I mentioned merging stars. So when both stars are in contact, they still want to keep growing because stellar evolution tells stars to become bigger. And eventually, we'll start losing mass from these outer Lagrangian points, remember? And when that happens, very quickly, the system becomes tidally unstable and the 2 stars will merge in roughly 10 days. So this is a simulation, a 3D simulation. It costs quite some computing power to do this, done by Fabian Schneider in 2019. And that's a very violent event, as you can imagine, causes a huge brightening of the stars, not quite like a supernova, but we would call this a red nova, for example, because it's quite red in color, and I guess not as bright as a supernova, as the name says. And this simulation in particular was very interesting because this was done in the context of explaining how magnetism occurs in massive stars. Normally, under normal conditions of single stars, for example, we don't expect a massive star to be magnetic because you need a convection zone to drive magnetism, and massive stars don't have that, at least not on the surface. But this simulation, this is again the same merging simulation, shows that previously non-magnetic material suddenly turns into extremely magnetic material. And this is again by like, I don't know what the orders, 7 orders of magnitude more magnetic. And so this could explain how we see that about 10% or 8% of massive stars are indeed magnetic. And in fact, I was part of this collaboration to look at this star here. There's a nice picture of it. The star in the middle is confirmed to be magnetic. And we actually see the nebula of all of the material that was thrown away in the merger that is still visible. So really, we caught this star just after it merged. Well, give or take a couple tens of thousands of years, right? That's really a nice result. And indeed, now, again, in our massive star community, we really have to think more carefully about, okay, if we see any massive star, would it have been 2 stars in the past because they might have merged? And that again plays into how we think it seeds the universe that changes. So why go into contact binaries? I hope I've given enough reasons. There's a lot of massive binary stars, essentially 100%. Most of them interact and merge, and that changes their properties and their supernova yields, for example. Furthermore, the properties of the merged stars depend on the physics in the contact phase. And that was sort of my job during my PhD, trying to figure out the physics of the contact phase and how that impacts on how we perceive and observe contact binaries. Furthermore, if we go outside of the massive star realm, there's also a lot of low mass stars because there's millions more low mass stars than there are massive stars in the galaxy. And they're very easily picked out of surveys like with Kepler and Tesla satellites that have been put up by NASA. So let's now take stock of all of the contact binaries, massive contact binaries in this case, that we have observed for now. It's not a lot. There's only about 20 odd stars in here, and that combines galactic stars as well as binaries in the Magellanic Cloud. But from the limited statistics that we have, you see that there's a reasonably broad distribution of equal mass contact binaries. So these are where the two stars have roughly the same mass, right, on this side of the diagram, as well as a whole bunch of contact binaries that have different size lobes, much like the one that I passed around here. Now, what do the models say? Well, the models predict this kind of distribution. So they overwhelmingly want equal mass contact binaries to be observed, and basically none in the low mass ratio regime. So this almost says like the lifetime of these kind of stars is so low compared to when they are equal mass that we shouldn't observe them there, and yet we do. So that's a bit of a problem. And you can start thinking about, okay, well, is there something wrong with our observations? Well, they're never wrong. I mean, whatever you see, you see. But we could be misinterpreted in some ways. When we look at data, contact binaries can actually be very easily confused with binaries that are just not yet in the contact phase. They might just be in front of it, not yet evolved enough. So that's something that we could be misinterpreting, or they could just be incomplete. It is estimated that we've only observed about 10% of all stars in the Magellanic Cloud. So there could be, you could make a case for saying that, oh, we haven't yet fully surveyed all of the possible evolutionary tracks, let's say, of massive star. Although it is hard to imagine that we're missing, for example, all of the non-equal contact binaries. So there's no good reason that only these stars we would not pick up versus the equal mass ones. So let's go to the other side and say that the models are wrong. And actually, I know that the models are wrong because models are always wrong, but some are useful. And this is one of the most famous quotes attributed to George Box, saying that when you make any model, you can make it as accurate as possible, but it'll never be granular enough to explain reality. Because if you have one of these stars, contact binary, a very complex thing, we have to make simplifications when modeling this. So what we usually do is we dumb this down into just spherical shells, make very harsh approximations of such systems, which may or may not be warranted. But that can introduce biases in our analysis. And during my PhD, I took stock of the models of contact binaries that we had and improved two facets of them to see if we could get a better match. First of all, stars are not spherical balls when you put them so close to each other due to tides right here. And also, when they are touching, you can exchange energy between one and the other. And those effects were ignored so far. So I set out to improve our models on this. Well, let's talk about tides first. I think you know tides quite well. It's caused by moon and the sun, differentially acting on the Earth. So the water closer to the moon gets pulled to the moon harder than the far side. And of course, if the Earth spins under it, you see the tides coming in and out twice per day. I believe the Delaware River has quite a strong tidal flow happening. So it's a good example of that. This is no different in stars. The closer part of the star gets pulled to its companion harder than the far side. Same in a contact binary. This side of the contact binary toward the companion gets pulled harder than the far side. And so that effect has to be taken into account when modeling. And so what this means is that rather than modeling spherical shells as we did before, we can actually, so this is the shortcoming. These areas, surface areas and contained volume, contained mass is actually poorly approximated in this model here. And that can affect things such as how big this star actually is versus how we model it to be, and so on. So my first project was to actually move away from this spherical approximation and go into another approximation where I actually allow the shells to be deformed by this Roche potential that I mentioned. And that is still possible to do in 1D, in one dimension, because you can keep the only independent variable here is the potential, essentially, the Roche potential of this shell. I did have to adapt the stellar structure equations a little bit before I could start my computations, but it is doable. And the main result is summarized in this figure, where as a star evolves in a binary system, it becomes bigger, as I said. It has to because of stellar evolution. But if you account for this deformation, you get the color tracks. And a star, which is in all other senses perfectly identical, it has the same mass, it has the same amount of metals, the same age, is actually roughly 5% larger versus when you model it as a perfectly spherical ball evolving in the same binary. And you could say, oh, well, 5% is not so much, but our instruments have gotten very, very accurate. We can measure radii and masses of stars to better than 3% these days. And so if you would compare these observations that are accurate to 3% with models that are only as accurate as 5%, you'll make a mismatch, you'll make a mistake. And so I urge now my colleagues to always use deformed stars when they want to compare to models rather than non-rotating spherical stars. So the next ingredient was energy transfer. And before I go into the details here, I want to distinguish between energy transport that happens within a star. So obviously, nuclear fusion creates energy, and that has to be transported to the surface, and that can be done either by radiation or by convection. In the sun, the first half is done by radiation, and then the second half is done by convection. But energy transfer is the term that we use to indicate energy flowing between stars. So transport is going from the center to the surface, and transfer is the process of moving between components. And this can only happen in contact binaries, of course, because you need a thermal connection between one star and the other. All stars, regardless of whether they're in contact, they do energy transport from the center, obviously, to their surfaces. Okay, now energy transfer is actually also not a very alien thing, because refrigerators and air conditioning do these things all the time. You move heat or energy from one side of your refrigerator to the other side using some pump and a working fluid, or the other way around. You can generate power with this by getting really hot water under pressure. This is a diagram of a nuclear reactor, for example. Move it to a turbine where it gets used to generate electricity, and then cool it down again using some cold water from a stream. So in a contact binary, this is actually not much different, because from observation, we see that if you again look at that model you looked at just now, the outer layers of a contact binary are actually very similar as you go across across the surface here, regardless of their mass. And that's quite important because in principle, from single star theory, you would say that a more massive star is hotter than a lower mass star, but that's not the case in contact binaries. They have almost exactly the same temperature. So we could, in principle, imagine that there is some kind of heat engine operating within this contact binary that acts to average out sort of the properties of two different stars across their surface. The problem is that we don't quite know exactly what the mechanism is. So unlike our nuclear power plants, for example, which we know pretty well, we don't quite know we don't quite know how heat is being moved. There's probably some flow going here. I haven't yet tried to model this. This would have to be done in 3D. There's very few approximations you can do here. So that will take a lot of computing time to figure out. Now, that was not the end of, well, this was essentially the end of my PhD thesis, but it's not the end of the story, because it could also be that we don't quite yet know how binary stars get born. So I mentioned that in the beginning, you need two stars being born closer together in an orbit than about 2 days. And this makes sense because if we look at massive stars, the period distribution of binary stars is roughly this blue line here. There's a lot of massive binary stars that have short periods versus not as much binary stars that have longer periods. And it turns out from the models that all of these blue ones here really like to form contact binaries that are equal mass. So if you take this area here, this sort of explains that a lot of massive binary stars create these equal binaries, which were overabundant to our observation, versus there's only a small sliver here of initial systems that will create unequal mass contact binaries. However, this distribution here, this blue line, could be a misinterpretation of our observational data, because it might well be that massive binary stars are born using this distribution, which has a much larger red area to produce unequal mass contact binaries. And there is some theoretical and observational evidence for what we call period hardening in massive binaries, where these two stars get born in a very massive disk of dust and gas, and this creates friction, bringing them closer together where they can actually form a contact binary. Because if the gas was gone here, they would never form a contact binary. For example, same thing here. If you have a third star, this can induce oscillations, causing a much tighter binary, where actually contact can be achieved. So going forward, we also need to rethink how we couple essentially stellar formation and binary formation to their actual evolutionary properties, such as the mass ratio, which we are still unsure about how it gets formed. All right, in my final part of my talk, I'll go into how we can use eclipsing binaries to also learn something on contact binaries. The term eclipsing binaries is actually reasonably simple. You just have to accurately measure the light, the total amount of light you get from such a star. You do this over a certain span of time, and you assemble all of these data points into what we call a light curve. I'm sure many of you might have already done this with variable stars, for example, like Cepheids, seeing them brighten and dim periodically. But binaries do a similar thing, because if you take a binary star that eclipses each other, you get periodically two dips as one of the star eclipses the other. And the ratio of the depths here can tell you something about the temperatures of the stars, for example. Because so right now, the less the cooler star is being eclipsed. Not as much light is being dimmed, whereas if you eclipse the white star, which is much hotter, you dim much more. You have a deeper eclipse. So these kind of properties tells us something about binaries, but we can go further, because if we then go through evolution of a binary system, the more massive star grows, and now our light curve is radically different. We still see the two eclipses here. There's this kink here and here, but there's a huge hump here, which essentially corresponds to the bigger star not being a sphere anymore. When you look at it from the side, it has a larger surface area than when you look at it from the back. And that corresponds to having more flux, essentially, when you look at the side versus when you look at it from the back, which is roughly here, just before the eclipse. Let's go even further and now also let the second star evolve and make a contact binary. That's roughly right here. And now you can almost not see the eclipses anymore. It's a very, very smooth curve. And whenever observers see such a light curve, they immediately think, oh yeah, that has to be a contact binary, because I don't see this kink anymore where the eclipse starts and stops. So again, we have observed hundreds of thousands of these contact binary light curves using the Kepler satellite and the TESS satellite. In upcoming years, there will be the Plato mission, which are all essentially variability machines. They can scan the sky very efficiently, making light curves of stars. But okay, well, yeah, this is my contact binary orbiting, but we can do more. Again, we want to learn how contact binaries work, what the physics is. And for example, we know that in such a contact binary, there can be mass transfer and energy transfer. So let's model that on the surface and I increased the contrast here a little bit so you can see it happening. Imagine that there is a gas stream from the hotter star moving over the secondary, over the right-hand star, creating this kind of spot here on the front side. Did you see how the light curve changed? This bump here is actually now higher than the second bump. See that? And not all contact binaries show this. And this really tells us something about what might be going on with stars like this. So there is most likely, this is not the only model, of course, but this is most likely where there's hot material from the hotter star traveling over the secondary star and cooling in the meantime. Because on the backside, it's not as prominent as it is on the front side. And such information, and this is exactly what we see, for example, again, when you train a telescope on it for months, this is a light curve that was obtained by Kepler, and I studied this in collaboration with Andre Persha at Villanova, and produced a very nice, produced a very nice model fit for this very star. And I want to say that the parameters of this light curve here is very much like the little model that I passed around. So there's this, or most likely, this kind of stream going across the binary. You have to imagine a swirl of gas going around this lower mass star. This is part of an SF project that Andre won a couple of years back. And we're gonna continue working on these kinds of light curves, producing much larger models, and in doing so, learn something about how contact binaries can be understood, both from their evolution side, as well as how their surfaces might be studied. Okay, that's most of my talk done. I hope that you take away from this that essentially all massive stars in the galaxy and indeed in the universe are part of multiple systems, in particular binary systems. That's the right-hand side of the diagram here. A lot of them do what's called binary interaction. A large fraction of them go through contact phases. And these contact binaries eventually merge, not only making beautiful nebulae, but physically altering properties of what we used to think of as single stars. There is a large discrepancy, unfortunately, in how the models predict the properties of contact binaries versus how we actually observe them. And obviously, we're still working on that to resolve that. But I guess the best is yet to come. We have improved slightly our models on the evolution front. We know that probably binary formation is not to be decoupled from binary evolution. And finally, the details of the light curves that such systems present to us might actually teach us something about the structure and even the evolution of such contact binaries. And with that, I'll close and leave the room for questions.
Good, thanks. That was a great talk. Any questions?
You mentioned during the talk about the increase in the magnetism, like by 7 orders of magnitude.
Right.
What's the theory behind why that's
Yeah.
occurring?
Sure. So wait, can I go back to that? Here. So it comes down to effectively the right-hand star being completely ripped apart, and that creates what we call the magnetic rotational instability, where magnetic field lines get wound up around each other so hard that locally at least. So initially you see that only the very edge of this star gets magnetized, but eventually all of these curling magnetic fields get wound up on each other, almost like a ball of yarn, until you get this big ball here. Now, eventually, this magnetic field will decay. We don't yet know how long that would be, over what time scale that would be. But on the formation side, we know pretty well it's because of the extreme rotation and shear and this magnetic instability that drives magnetic field lines to become wound up, essentially.
Does the sort of composition of the star change? Like, are there more metals involved because of the magnetic field or anything?
No. So in this event, it's still just hydrogen, but of course, because there are a lot of free charges that are that can travel, that's enough to generate magnetism on its own.
Okay.
You don't need any magnetic material or anything for that.
Thank you. Are there distinct poles observable during the cycle?
That I don't know. So I'm not familiar with exactly how you observe a magnetic star. We do this with the technique called spectropolarimetry. I guess there would be indeed a north and south pole associated to such a star. Probably as you imagine the rotation of this star being in a plane, the north pole will probably be on the north, just like on Earth, and the south pole on the side, on the other side. So yeah, this is obviously not a monopole, for example, because those things don't exist in physics.
Between the start of binary interaction to the start of binary contact, how long does that usually take?
That can vary. So in the example that I gave here a while back, it'll be about, again, we like to use the term 1 million years because, again, the lifetime of a massive star is roughly 10 million years. So if where is it? If they get born let me just move to it quickly. If they get born at 1.4 days, oops. If they get born at 1.4 days, it takes roughly 1 million years for the binary interaction to start, and then another 1 million years before they get into contact. And then they will stay in contact for, let's say, 3 to 4 million years for essentially the rest of their main sequence lifetime. And then they'll merge.
Have you factored in, like, each star is gonna be rotating,
Sure.
and do they always rotate like the same direction or in opposites?
Yeah, so we expect that for massive stars that have a period shorter than, let's say, roughly 10 days, roughly 5 days, the tidal forcing is so strong that they rotate what we call synchronously, so they'll be tidally locked almost immediately. When you go longer than 10 days, that's where this transition period happens, where they're still sort of free to rotate, but there'll be this tug, much like the moon does on the Earth. The Earth is slowing down because of tides. But it's a very strong function of period, of orbital period. If you're shorter than 10 days, tidal synchronization is pretty safe bet. If you go longer to, let's say, 20 days, not quite sure. Above 20 days, it's essentially free rotation because tides are not that strong at far distances.
Thank you.
You mentioned earlier that most of these giant stars are found in pairs.
The massive stars, yes.
The real massive stars. As they go through this process,
right,
it would seem that at the end of the process, there would be remaining single massive stars. Do they then find each other? Or why isn't there a greater population of solitary massive stars?
That's a very good question. Probably, how should I answer this? It still comes down to lifetime. So when you have a whole population, let's say a new galaxy gets formed, or a new cluster gets formed of stars. The first thing that'll happen is where you have two stars separately, right? And then only after roughly 10 million years or so, lots of these stars will have merged. Not all of them will merge. They will stay binary for the rest of their lives. You still have binary black holes that can come from this, and these orbit each other for not millions, but billions of years. But you won't see them because they're not stars anymore. But in fact, again, in our community, when we see a massive single star, we really sort of squint our eyes a little bit and say, this is not normal. So when we look at this single star, we first usually look at the neighborhood. Is there something still around it? It might be one of these triple star cases where there is a really far third star going around the binary, which won't interact, but then the inner binary doing its thing, going through the evolution and merging. And that's how this magnetic star was formed.
Blue stragglers would be an example of that, right?
That's right.
It's very spectroscopically unusual.
Yes.
To find them.
That's right. So when you look at a star and you wince your eye, you squint your eyes and you look at them very carefully, they'll probably have different properties than what you expect a star to have, for example, to be on the main sequence. It will not be on the main sequence. It will be way to the left of it or way to the right of it. It'll have peculiar properties. Also, it will have more metals on its surface, for example, than a typical main sequence star.
So would magnetic A stars be an example of this?
I'm not sure, because those can also be forming stars, where they are still contracting and inheriting the magnetic field from the cloud they were born in.
Because they often have very interesting spectra too, with heavy metals.
Sure. Yeah. Magnetic
Stuff that I consider metals, not astronomer metals.
Great talk, thank you.
Thank you.
Are there any binaries with mass transfer that we can actually see in our telescopes?
That's a good question. The one that I can think of is Algol. Algol is observable at least with very large telescopes, because the thing is, this happens on such a small scale on the sky that you need a very big telescope, probably even interferometer, to be able to resolve such a tiny scale. So I don't think that with amateur equipment or any equipment under 10 meters, because again, I think you need.
I've only got an 8 meter, sorry.
Yeah, it's not. You need an interferometer to go that way. I believe,
What about Beta Lyra? Isn't that a contact binary or close to?
I'm not sure. But Algol, I think, is the one that is definitely interacting and mass transferring. So this is the picture here. So this, I think, is an interferometric measurement. Yeah, using the Chara interferometer, where, you can't see it, obviously. Let's move that over. Yeah. It's not that easy to see in this light, but there is one star here orbiting the secondary star, and actually it's the dimmer star that is the mass donor here. It's somewhat extended and a little bit cooler than Algol B, and it is donating mass, but you can't see the stream or anything. That would be too dim, making the central star here more and more massive as it goes along.
What's the period of Algol?
I don't know by heart, but that can be
3 days.
Yeah, that can be more than 10 days. Yeah.
Beta Lyra is 12 days.
So there will be several of them going through this slow mass transfer phase that takes millions of years, or even billions, I guess, if for low mass stars. But the problem is the resolving power that you need to actually see the two components.
I had a question, not about the stars interacting with themselves, but how they interact with other objects in their star system. Given that there are now 2 stars in the system,
right?
Does that move out the habitable, quote unquote, Goldilocks zone of that star system? Does it move further out?
Yeah, so that obviously depends on precisely what the masses of the individual stars are. If you have, much like in Tatooine, you have one very massive star and then one probably wimpy low mass star that isn't as bright, you can almost approximate it as if the second star wasn't there, because it's not moving, it's not creating that much heat.
So it'd be like this habitable zone of that system would be kind of similar to Earth's.
Yes. That's I think how Tatooine was imagined in some sense. But on the other hand, if you have 2 very similar stars like the sun, if you have 2 suns literally next to one another, that would obviously push the habitable zone out, because there's now twice the amount of irradiation going through that solar system. And I think that would move your habitable zone by the square root of 2 outward, because of the square law, obviously. So yeah, but that definitely has an effect. Although more importantly, because you have a binary star, your planets can never be too close to the stars either, because that's dynamically unstable. The third body needs to be at least, I don't know what the number is, 5 or 6 times farther away than the separation of the 2 stars to still be able to orbit it stably. So that might also put a limit on where you can put planets inside of a binary system.
Are there many or any 3 or more star binary?
Oh yeah, absolutely. Yes, actually, that diagram that I showed you, let's go back to, where's my mouse? The diagram that I showed you here. This is actually a bit of a simplification, because the term here says multiplicity. This combines all of the possible configurations more than 2. So this can be 2 stars, 3 stars, 4 stars, 5, and even higher. Although I think we don't go further than 4. But it turns out that if you go again at the massive star end, the average number of companions per massive star turns out to be 2.1. If you do the statistics. And so that means that on average, a massive star will be part of a triple system. So 2 stars in the middle probably, with a third one going around it in a much...
In actually in contact with?
No, the third star is so far away that it doesn't affect really the evolution of the inner 2. The inner 2 can be in contact, although I don't know actually whether we've observed or observed all 3 components of such a system. We have a pretty good idea that when you see a contact boundary, there must be a third star somewhere around, but we haven't yet found a definite signature of that third star.
Great. Any other questions? All right, if not,
The last one.
NGC 2017 is considered to be a multiple star, sometimes called an open cluster. Is there a delineation between the two that at some
Yeah.
point you're not gonna have? Is there a upper limit to the number of stars that could be in a
Right.
multiple star system?
Yeah, so I think at some point when you go out enough from your primary star, it is hard to still call it bound to that star, because eventually the gravitational pull of the rest of the cluster will start contributing more. And that's, I guess, where you would put the boundary. But for me, to be honest, I put the boundary at where you interact or not. Because if you have two stars that are far enough apart, they might orbit each other, like with an orbit of, I don't know, 10,000 years. They will not influence each other meaningfully. So you might as well consider them single, at least from an evolutionary perspective. I'm a modeler, and when I want to model these stars, I don't have to bother about the binarity. So I guess in practice, this means that any star with any binary pair with an orbit larger than roughly 10,000 days can be considered single. They're still bound. And if you go way, I don't actually know where the limit would be where they would actually be unbound. I guess it becomes roughly the scale of an open cluster. I'm not familiar with those scales as of yet, but that would be fractions of a light year, I would assume. So.
Thank you.
it's a dangerous question. It's like, what's a planet and what's not?
Yeah.
Is it a multiple star or an open cluster?
Mhm.
All right, let's thank Matthias for a great talk.
Thanks.
I heard Jeremy owed you dinner for this, right?
He owes me deadlifts.
And dinner after that.
Well, thanks for coming out tonight. It's a great talk.
I'm curious.
Right.
Have a safe drive home.
Which book do you recommend?
The merge table still open.
If you wanna get, so
Everybody.
you wanna go into like really deep science?
Next Star Watch. And you're again.
Okay.
Take care.
Okay,
But last night?
I actually know what I was sleeping.